Polymer photochemistry, light-driven generation, transformation, and degradation of polymers. Polymers exhibit diverse interactions with light that can either facilitate polymer synthesis and functional transformations or induce degradation and depolymerization. Understanding the conditions governing these processes is critical for developing advanced materials and sustainable end-of-life strategies for plastics. Recent advances in polymer photochemistry have enabled light-mediated polymerization, functionalization, and controlled degradation. These processes operate under mild conditions, often with visible or ultraviolet (UV) radiation, providing unique advantages in areas such as additive manufacturing, biomedical materials, and environmentally responsive polymers. Polymers display unique photochemical behavior when exposed to light. In some cases, light provides the energy required to generate polymers or trigger new chemical transformations under mild conditions. In other cases, photochemical interactions can cause polymer degradation or promote depolymerization. Careful control of these interactions can therefore be used either to improve polymer performance or to facilitate controlled degradation, which is particularly important given the increasing demand for photodegradable materials. The design of photodegradable polymers requires the identification of photoresponsive materials with desirable physical properties. For biomedical applications, the development of biocompatible photoresponsive polymers and suitable light sources is essential to minimize toxicity while enabling controlled degradation or activation. Synthetic polymer photochemistry has expanded rapidly in recent years. Since approximately 2010, the number of studies combining polymer chemistry with photochemical methods has increased significantly. Photochemistry is attractive because photons can transfer substantial energy to molecules, enabling reactions that are difficult or impossible under conventional thermal conditions. Energy considerations in photochemical processes. Modern polymer photochemistry typically employs visible light, 380 to 700 nanometers, or ultraviolet radiation, 200 to 380 nanometers. The energy delivered to a molecule upon photon absorption can be estimated using the Planck equation. In contrast, thermal energy available from the surrounding environment can be approximated using Boltzmann's constant. Although this relation strictly applies to ideal gases, it provides a useful estimate of the thermal energy available to molecules in solution or solid phases. Photons in the visible and near UV regions possess energies several orders of magnitude greater than the thermal energy available under typical laboratory conditions. However, thermal energy is accessible to all molecules in a reaction mixture, whereas photon energy is absorbed only by molecules that interact with light. Consequently, a continuous photon flux is required to sustain photochemical reactions. The high energy delivered by photons enables a wide range of chemical transformations in polymer systems, including polymer synthesis, post-polymerization functionalization, and degradation. Photopolymerization. Historical development. Light-induced polymerization has been recognized since the 19th century. In the 1840s, irradiation of styrene was reported to produce glass-like materials, long before the concept of macromolecules or radical polymerization was established. By the early 20th century, these reactions were understood as chain processes, with studies demonstrating increased formation of poly-vinyl bromide under light irradiation. Although photopolymerization has existed for more than a century, the field has expanded significantly over the past decade. This growth has been driven by developments in controlled polymerization techniques involving reactive cationic and radical intermediates, as well as the emergence of additive manufacturing and 3D printing technologies. Advantages and industrial applications. Photopolymerization is widely used industrially to produce functional coatings, surfaces, and chlorinated compounds. A key advantage is the ability to generate reactive species at ambient or even subambient temperatures. This reduces energy consumption and allows polymerization of systems with low sealing temperatures where thermal polymerization may be thermodynamically unfavorable. Photochemically generated reactive species. A variety of reactive intermediates can be generated through photochemical processes, including radicals from classical photoinitiators, radicals produced via carbon-sulfur bond cleavage in the photoinverter process, radicals generated through photocatalytic energy or electron transfer in photoinduced electron, energy transfer, reversible addition, fragmentation, chain transfer, PET raft, polymerization, photochemical reduction of copper. 2. Deactivator complexes in atom transfer, radical polymerization, ATRP. cations in photocationic polymerization, photoacid activation of metathesis catalysts, photochemical activation of monomers in ring-opening metathesis polymerization, ROMP. Because photochemical processes are largely independent of temperature, these reactive species can be generated efficiently under mild conditions. Reaction kinetics and light intensity. In radical photopolymerization, the steady-state concentration of radicals is determined by the balance between photochemical radical generation and termination processes. Consequently, the polymerization rate is directly influenced by light intensity. Studies of both free radical polymerization, FRP, and raft-based systems, including PET raft, demonstrate that polymerization rates scale with light intensity. Temporal and spatial control. Photopolymerization provides precise temporal control because reactions proceed only in the presence of light. On-off, experiments demonstrate that polymerization occurs when irradiation is applied and ceases when the light source is removed. In the absence of photochemical activation, radical or cationic intermediates rapidly deactivate or recombine, terminating chain growth. This property enables spatial and temporal control of polymer formation, which is essential for applications such as patterned surfaces and 3D printing. Photochemical functionalization. Cycloaddition reactions. Cycloaddition reactions involve the interaction of two or more pi-electron systems to form cyclic products. Two prominent examples are the 4+2 and 2+2 cycloaddition reactions. According to frontier molecular orbital theory, these reactions occur through interaction between the highest occupied molecular orbital, HOMO, of one reactant and the lowest unoccupied molecular orbital, LUMO, of another. Proper symmetry matching between these orbitals is required for reaction. The 4+2 cycloaddition, exemplified by the Diels-Alder reaction, occurs readily under thermal conditions. In contrast, 2+2 cycloadditions are symmetry forbidden thermally and therefore require photochemical activation. Under irradiation, two unsaturated pi systems undergo photoinduced 2+2 cycloaddition to produce four-membered cyclic structures through either concerted or stepwise radical pathways. Thiol-X click chemistry. Thiol-X reactions represent versatile coupling reactions between thiols and functional groups such as alkenes, alkanes, or alkyl halides, forming CS bonds. These reactions are widely applied in polymer synthesis and modification and are recognized as click chemistry transformations. Common examples include thiol-ENE reactions, thiol-wine reactions, thiol-Michael additions. These reactions enable the construction of polymer networks and advanced architectures such as hydrogels, dendrimers, and hyperbranched polymers. Photoinduced thiol-ENE and thiol-wine reactions are particularly useful in biomedical applications, including hydrogel formation and polymer drug conjugation, because they offer excellent reaction control and low cytotoxicity. Photodegradation of polymers. Importance and environmental context. Photodegradable polymers have attracted increasing interest both for enhancing polymer stability and for enabling controlled degradation. Photodegradable materials are particularly relevant to environmental sustainability and targeted drug delivery. Global plastic production reached approximately 400 million metric tons in 2022, leading to a continuous accumulation of plastic waste in the environment. Incorporating photodegradable functionality into polymers has therefore been proposed as a strategy for mitigating long-term environmental persistence. Unlike thermal or chemical degradation processes, photodegradation can occur gradually under sunlight or artificial light sources, offering a potentially greener approach to polymer breakdown. Mechanisms of photodegradation. Photodegradation occurs when photons interact with chemical bonds within a polymer, causing bond cleavage and generating smaller molecules or oligomers. Polymers containing photoactive functional groups such as ketones, nitrobenzyl groups, coumarins, or anthracenes can undergo main chain or side chain cleavage upon irradiation. Vinyl ketone-based polymers represent a notable example of photodegradable materials. These polymers degrade rapidly under UV irradiation through Norrish-type photochemical reactions associated with ketone side chains. Homopolymers of phenyl-vinyl ketone exhibit properties similar to those of polystyrene but degrade more readily under light exposure, making them potentially more environmentally favorable. In addition to homopolymers, cleavable units can also be incorporated as side chains or degradable blocks within polymer architectures. Photoinduced discoloration and loss of function. Exposure to light can negatively affect polymer performance by causing discoloration, mechanical degradation, and reduced lifespan. Surface yellowing and loss of gloss are common indicators of photochemical damage, typically caused by UV absorption by additives, chromophores, or impurities within the polymer. Color formation in polymers arises mainly from two sources: structural changes within the polymer matrix resulting from side reactions during manufacturing or use. Formation of byproducts during stabilization processes as antioxidants and stabilizers transform during the polymer life cycle. These processes can significantly restrict the range of practical applications for polymer materials. Discoloration may result from polymer oxidation or from transformation products of stabilizers such as hindered phenolics and aralamine antioxidants. These products absorb in the visible spectrum and contribute to color formation. Mitigation strategies typically involve scavenging oxygen-scented radicals to suppress oxidative degradation. In aromatic polymers, benzenoid structures can act as pro-oxidants, leading to the formation of quinoid compounds, stilbene quinones, and aromatic carbonyl derivatives such as acetophenones, benzophenones, benzoates, vinyl benzoates, and diketones. These oxidation processes often involve hydrogen abstraction and hydroperoxide formation, ultimately causing chain scission and crosslinking. For example, polyethylene terephthalate, PET, exposed to thermal and UV conditions undergoes hydroperoxidation reactions in which hydroxyl radicals attach to aromatic rings, producing yellow-green colored oxidation products. Photo-enhanced depolymerization. Depolymerization has become a major research focus because recovering monomers from polymer waste is critical for sustainable plastics management. Conventional depolymerization typically requires heating a polymer above its sealing temperature, where depolymerization becomes thermodynamically favored. The removal of volatile monomers, such as methyl metaacrylate, can shift the equilibrium toward monomer formation even below the sealing temperature. Photochemical activation can further enhance this process by generating reactive intermediates, such as radicals, within polymer chains. These species accelerate depolymerization or allow it to occur at lower temperatures. Light-driven activation also enables spatial and temporal control of depolymerization processes. Conclusions and future perspectives. Polymer photochemistry continues to evolve as new photochemical strategies enable polymer synthesis, functionalization, and degradation under mild conditions. These processes offer several advantages, including reduced energy requirements, precise temporal and spatial control, and compatibility with sensitive biological systems. Emerging applications include photopolymerization for additive manufacturing, spatially controlled material modification, and environmentally responsive polymer systems. Ongoing research is expanding beyond simple temporal, on-off, photochemical control toward complex spatially resolved polymerization processes required for advanced manufacturing techniques such as 3D printing. Photochemical functionalization is already enabling the creation of surfaces with finely tuned properties. Furthermore, improvements in high-intensity and cost-effective light sources, including the use of direct sunlight, are expected to simplify and broaden the practical implementation of polymer photochemistry in the future.